Hi guys! Welcome to the second part of the lecture on improper integrals. Once again, I am Dennis Layson. For this part, we deal with improper integrals whose integrand has an infinite discontinuity on the given interval. To introduce such integral, let us consider the region R bounded above by y equal to 1 over the square root of x, bounded below by the x-axis, and between the lines x equal to 0 and x equal to 1. Observe that the function 1 over the square root of x has an infinite discontinuity at x equal to 0. Geometrically, that means this graph is asymptotic to the y-axis, and hence the shaded region extends infinitely up in this direction. What is the area of this region if the area is finite? Well, intuitively, as a definite integral, we can say that the area of this region is the integral of 1 over the square root of x, evaluated from 0 to 1. However, we cannot evaluate this definite integral using the fundamental theorem of calculus because of the fact that the integrand has a discontinuity at x equal to 0 from the right of 0. So how do we make sense of this integral? Well, we can take a finite portion of the region R. That is by taking any number t between 0 and 1 and consider the region bounded above by y equal to 1 over the square root of x, below by the x-axis, and between the lines x equal to t and x equal to 1. Clearly now, this function is continuous on the interval t1. Hence, its area, if I denote by a sub t, is equal to the definite integral of 1 over the square root of x from t to 1. And because the function is continuous on this interval, we can use the second fundamental theorem of calculus. That is, we find an antiderivative, which in this case is 2 times the square root of x, and we evaluate from t to 1. So we get 2 minus 2 times the square root of t. Now to get the area of the entire region R, what we do is we let this t move towards 0 from the right of 0. That is the same as taking the limit as t goes to 0 from the right. Now when we solve for the limit of a sub t, as t goes to 0 from the right, that is equal to the limit of 2 minus 2 square root of t as t goes to 0 from the right. And clearly, the square root of t tends to 0 as t goes to 0 from the right. Hence, this gives us a finite value 2. We define the area of the given region R as the limit of a sub t as t goes to 0 from the right. And therefore, although this region is infinite, it has a finite area, which is 2 square units. We simply write in this case the limit of the integral from t to 1 as t approaches 0 from the right simply as the integral from 0 to 1. Hence, we can now define improper integrals with an infinite discontinuity. So first, suppose that function f is continuous between a and b, continuous from the left of b, but there is an infinite discontinuity at x equal to a. What we do is we replace this a by some variable t, we evaluate the integral from t to b, and then later we take the limit as t goes to a from the right. In a similar manner, if we have a function f continuous between a and b, continuous at a from the right of a, but there is an infinite discontinuity at b, then we simply replace b by some variable, say t, evaluate the integral from a to t, and then get the limit as t goes to b from the left of b. Of course, this limit must exist for this improper integral to have a value. In such case, we say that the improper integral is convergent. But in the case that the limit does not exist or is infinite, we say that the given improper integral is divergent. Let's take a look at some examples. In this example, we consider the integral of the function 1 over the square root of 16 minus x squared, evaluated from -4 to 2. At first glance, this problem looks ordinary. However, when you inspect continuity of the given integrand, it actually has an infinite discontinuity at x equal to -4. But for values of x greater than -4, but less than or equal to 2, the function is continuous. So because of the discontinuity at the lower limit of integration, this is an improper integral. And by definition, we write this in the following form. So we replace this -4 here by the variable t, and then we get the limit as t approaches -4 from the right. Now this integral can be evaluated using the fundamental theorem of calculus. So find an antiderivative, evaluate from t to 2. You can verify that this will give you the limit as t approaches -4 from the right of sine inverse x over 4 evaluated from t to 2. And when we do the evaluation of the function, we get the following. This is the value when x is equal to 2, and this is the value when x is equal to t. Now, if we want the limit as t goes to -4 from the right, this is what we get. Sine inverse 1/2 is constant, and as t goes to -4 from the right, this value tends to -1, and so we get sine inverse of -1. Sine inverse of 1/2 is equal to pi over 6, and sine inverse of -1 is equal to -pi over 2. This gives us 2 pi over 3. Now, because the limit exists, the value of the improper integral is equal to 2 pi over 3, so we say that the improper integral is convergent. For our next example, consider the integral of tangent of x from 0 to pi over 2. Again, here we inspect continuity of the tangent function. We know that the tangent function has infinite discontinuities on odd multiples of pi over 2. Hence, this is continuous from 0 to values of x less than pi over 2, and there is a discontinuity at pi over 2. So again, by definition, what we do is we rewrite in the following form. Replace pi over 2 by some variable t, and we get the limit as t goes to pi over 2 from the left. Again, this integral can be evaluated using the fundamental theorem of calculus. An antiderivative for tangent of x is ln of the absolute value of secant of x. We evaluate this from 0 to t. We get the following expression. Note that ln secant 0 is equal to 0 because secant 0 is 1 and ln 1 is 0. So this leaves us with the following limit. Now let us look at the behavior of the secant function. As t goes to pi over 2 from the left, this secant function tends to infinity. Because recall that secant is 1 over cosine, and as you approach pi over 2, the cosine goes to 0, and 1 over 0 as a limit form is infinite. Now this thing goes to infinity, meaning we move to the right, and as we move to the right, the natural logarithmic function increases without bound. So this gives us an infinite limit. This improper integral has no value, and therefore, it is divergent. Now what happens if the discontinuity is located somewhere between the limits of integration? In such case, we just have to partition the given integral into two improper integrals. If this function f has a discontinuity at a number c between a and b, and it is continuous everywhere else, we can write the integral from a to b as the sum of the integral from a to c and the integral from c to b. For this given improper integral to be convergent, both improper integrals on the right-hand side must be convergent. If at least one of these two improper integrals on the right is divergent, then the given improper integral is also divergent. Let's consider this particular example. Let's integrate 1 over the cube root of x minus 1 from negative 7 to 9. Inspecting continuity, it is discontinuous at x equal to 1, and 1 is between negative 7 and 9. It is continuous everywhere else. And so, we have to partition this as a sum of the integral from negative 7 to 1 and the integral from 1 to 9. Now, all we need to do is to evaluate each of the integrals on the right-hand side if those values exist. So on one hand, we have this improper integral. The discontinuity occurs at 1. We replace 1 by some variable, say b, and then we get the limit as b goes to 1 from the left. Again, this integral can be evaluated using the fundamental theorem of calculus. You can verify that an antiderivative for 1 over the cube root of x minus 1 is 3/2 times x minus 1 raised to 2/3. So we evaluate this from negative 7 to b. That will give us the following. This is the value when x is equal to b, and this is the value when x is equal to negative 7. Now we take the limit of this function as b approaches 1 from the left. Clearly, b minus 1 will tend to 0. So this vanishes. This gives us a finite value, negative 6. So one of the two integrals on the right-hand side is convergent. We check the other integral. Now, the integral from 1 to 9 has a problem at the lower limit of integration. So we again replace that lower limit of integration by some variable. In this case, I am using a, and then we get the limit as a approaches 1 from the right. Same process. We evaluate this using the fundamental theorem of calculus. Of course, we may use the same antiderivative, this time evaluated from a to 9. We get the following expression. This is the value when x is equal to 9, and this is the value when x is equal to a. This time, when a approaches 1 from the right, a minus 1 tends to 0. So after limit evaluation, this term vanishes and we get 6, which again is a finite value. Since both integrals on the right-hand side are convergent, then the given integral is also convergent, and its value is equal to the sum of the values of the improper integrals on the right-hand side. So negative 6 plus 6 is equal to 0. For exercises for this particular case, you may answer the following on your own, and you may watch the discussion video for this part. That concludes the lecture on improper integrals. Thank you very much for watching.